Okay, great. Thanks, Rebecca. I'm going to turn back to the slides and we're going to jump into, again, there's a summary slide on 49, just kind of wrapping everything up from that particular example. But again, very good performance of the adjustment. And again, like a standard weighting approach would just completely miss the boat. And that's kind of the message here. So, okay. All right. So the third example is also using the MUBP, but we're using a completely different context. So we've had a couple examples using the household pulse survey now. So we're going to shift to a completely different context involving polling, where there's a more difficult to define target population, and we're working with completely different data sources. Okay, so we're still using the MUBP, but completely different application. So we're looking at the proportion of likely voters in Wisconsin who voted for candidate Trump in the 2020 presidential election based on a particular poll that was conducted at a particular point in time. So it's you guys are all familiar with the horse races and things like that. It's very popular to say, look at what this poll is showing, and I wonder if that's what's going to happen, and seeing like if we're getting a good sense of what might happen based on a given poll. This is applying the MUBP idea to one of those polls, which again had a very, very low response rate and can be thought of as a non-probability sample. So that's the application here. These are just some comics that Rebecca came up with about polling, and just kind of classical thing like poll workers, very, very difficult job. Talking about how many people don't trust polls. It's a very complicated industry to work in, especially nowadays. So, okay, so we're analyzing polling data that Rebecca and I examined in a 2023 Public Opinion Quarterly paper. The indicator was intention to vote for candidate Trump. So that's our binary dependent variable of interest. The non-probability sample in this case was a pre-election poll for the 2020 U.S. presidential election. It was conducted in Wisconsin by ABC and the Washington Post. The data collection was actually performed in close to the election by Apt Associates, so September, October 2020. And again, the challenge population-wise is we're specifically focusing on likely voters from that pre-election poll. So not all people who are eligible to vote, but likely voters. The goal was to estimate the proportion of likely voters who will vote for Trump. And the problem is that Trump supporters may have been less likely to participate in a pre-election poll. Again, a classical example of non-ignorable selection bias, which in this literature is called a partisan non-response bias. So the idea that a particular candidate's followers are going to be much less likely to participate in these kinds of polls. So again, like with the vaccine example, just a classic example of the non-ignorable selection scenario. Okay, another break for a comic. Again, the difficulty of poll workers, where the guy says, damned if I'm telling you if I'm actually undecided or not. So always a challenging problem to measure vote preference. Okay, so the sample data, the poll in this case is again technically a probability sample. It was conducted using dual frame probability sampling of landline and cellular telephone numbers. We are considering it to be a non-probability sample because very similar to the HPS, the response rate was under 7% in this particular case, despite the dual frame application. And we're only focusing on the subsample of likely voters who met these three criteria. They had either already voted, including early voting by absentee, they were registered to vote, and they self-reported in the survey at least a 50-50 chance of voting, or they indicated that they would register to vote by election day and self-report at least a 50-50 chance of voting on election day. So there are many different ways in the literature to define likely voters. This is just the application that we use for this particular context. So we also had to identify the population data sources of likely voters using similar criteria. So a more challenging population. So tiny sample. Unlike the HPS, where the non-probability sample was of size 65,000 or 74,000, depending on the estimate, in this case, the resulting respondent sample was 803 people in the state of Wisconsin. So very, very big difference from kind of the big data scenario we were talking about earlier. Most of these political polls are at about 1,000 or lower when they're conducted. The outcome of interest, again, the binary Y was an indicator of intention to vote for Trump. And we used pretty similar covariates to what we saw in the HPS example, but with some different examples thrown in. So we have sex, we have age, we have education, we have race, ethnicity, all of those being categorical. But then, given this application, we're bringing in a couple Z variables that we believe are going to be strong predictors of this particular binary variable. So that includes political ideology, liberal, moderate, or conservative, and then party identification, Democrat, Republican, independent, or other. Now, it seems on the surface like, of course, those would be strong predictors of whether or not you're going to vote for Trump. But the key point here is that we also have to find those same Z's in a population data source. And honestly, that was probably what took the most time in this particular case study, was vetting different potential population data sources that may or may not have had these same Z variables available to use and to harmonize. So as part of the study, we actually looked at multiple different potential population data sources, all from some form of probability sampling. In the poll itself, like in the HPS, final survey weights were computed for all of the poll respondents. Those final survey weights were based on probabilities of selection, based on their self-reported landline and cell phone ownership, and they were also calibrated to known population control totals on selected demographic variables. And those were derived from the National Health Interview Survey and the US Census Bureau. So very careful attention to detail, going by the book in terms of the way the weights were computed based on the probability sample. And we're going to use those in the analysis again to see how well they perform. We've included a couple links here for more details on the weighting methodology from ABC News. And then other information about the probability sample design is available in the documentation for the poll, which you can find at the PARC pre-election polling archive. So all these data are publicly available. Okay, so for this example, we look at an unweighted estimate of the proportion voting for Trump. We look at a weighted estimate of the proportion voting for Trump using those weights that were computed for the poll. And then we're going to jump right to the MUBP adjusted estimate of the proportion voting for Trump. So we're not showing the actual bias measures. We're jumping right to that fourth step of just adjusting the unweighted estimate. And as a reminder, again, we interpret the MUBP as being the difference in proportion. So we can talk about bias in terms of percentage points without that need for standardization. Now, coming back to the population source issue, again, our target population was likely voters in Wisconsin. Challenging to define, dynamic, definitely not stable, unlike the HPS target population definition. The population level covariate summary statistics that we need for the MUBP were obtained from the American National Election Study, or ANES, in the end. We also considered two other probability-based survey sources that we found were not as effective as the Z variables were available in the American National Election Study. So this was a probability sample of voters from the state of Wisconsin that was taken prior to the election. So that's a key aspect, is the probability sampling. We looked at calibrated sample weights that were provided to compute these population level means, variances, and covariances. We're going to show that in R in a second. We're going to show how we did that manually. And we needed to ensure that all of those Z covariates were binary indicators and exactly harmonized with the variables that were computed in the ABC polling data. So that harmonization step is essential. So the covariates include demographics, political ideology, and party. And as I said, some of them might be highly relevant predictors of voting patterns in the US and are likely to be highly correlated with an indicator of voting for Trump. So again, we're going to evaluate that proxy strength and compare that to the performance of the resulting inferences that we're making. Like the HPS vaccine example, we also had a benchmark truth for voting outcomes in 2020 for this particular case study. So the actual voting outcomes are available on a public use archive from the MIT Election Data and Science Lab. So we've included a link to that here where we got the final vote outcomes for each of the states. So the true proportion who voted for Trump in Wisconsin in the 2020 election was 48.82%. So we know that to be our benchmark, and we can use that to evaluate the performance of these different methods. And like in the vaccine example, the poll estimates, something that also received an absolute ton of media attention in 2020, were horribly biased in Wisconsin. So the performance varied across states, but they did really poorly in Wisconsin. So the question was, can the MUBP approach, again, produce adjusted estimates that are approaching the 2020 election outcome for the state of Wisconsin? So a similar roadmap, we're going to calculate the weighted and unweighted estimates based on the selected sample. We're going to get the summary statistics for the non-selected sample from the ANES. We're going to calculate that MUBP index using a Bayesian approach. And then we're going to calculate that adjusted proportion based on the draws of the MUBP following that Bayesian approach. And we'll also look at the strength of the proxy, which is again written incorrectly here. We definitely have to fix that, but that should be rho hat UX in this case. Okay, so back to R. Now I'm opening up example number 3, if you're following along at home. Okay, so we're bringing in one additional package here, Broom, that we need for the approach that we're using here. So I'm just going to make sure we have all those packages loaded. All right, we start with estimates from the selected samples. First, I'm going to read in and prep the sample data. So to start with, we're reading in data from the poll in Wisconsin from ABC. So that's the CSV file being read in here. We're just going to take a quick look at those data. So you can see the weight that was computed by the polling group. The state was Wisconsin, and then we have all these binary indicators. The Trump indicator, were you a male, all the age groups, etc. So those are all the binary variables that we're going to be using as predictors of that Trump indicator. So race, ethnicity, education, ideology, and then party identification. Okay, all turned into binary indicators. So this is the actual polling data here, including the weight. All right, so we have, again, same approach. Look at the unweighted estimates to begin with. We'll read in the polling data, not account for any weights, and see what we get. Okay, so when we run that analysis, we see that the unweighted estimate of the proportion that would vote for Trump among likely voters is 38.4% thereabouts. We see now a wider interval because, again, this was a smaller sample. If we're assuming simple random sampling, so there's a wider 95% confidence interval around that proportion estimate. So we see about 10 percentage points of bias, a little bit higher in terms of the actual known truth for how many likely voters in Wisconsin voted for Trump. So let's see if those weights that were provided by the ABC poll help at all again. So again, I'm going to specify the existing weight variable in that data file and then perform a weighted analysis and generate a confidence interval based on linearization for that. The weights hardly budged that estimate. So the observables that the weights were based on were hardly shifting that estimate at all. It went from like 38.8 to about 39.4. So here, the observables are not really fixing up anything. Okay, and in fact, what's happening is that confidence interval is getting wider due to the use of weights and estimation. So if anything, we're harming ourselves by using the weights in this particular case. We're just resulting in a more unreliable estimate. Okay, so in this case, the weighting adjustments, which I said, by the book, carefully calibrated, everything that you're supposed to be doing with weighted approaches didn't help in the slightest. Okay, so lots of stories, articles written in the paper. These polls are way off. They didn't perform well at all. All of the weighting adjustments, the pollsters like, we're trying everything we can with weighting. We're using this source. We're using that source. We're doing everything we're supposed to be doing. Weighting assumes ignorability. What every pollster is arguing about is always assuming ignorability. That's what keeps being missed by the polling industry. People are reluctant to go outside of that tried and true weighting solution to fix up these kinds of problems. If we allow for the possibility of non-ignorable selection bias, we can see what might be happening. Okay? So let's kick into that approach for MUBP. We're going to start by getting summary statistics for the non-selected sample from the ANES. And the difference in this code is we're showing you, rather than just grabbing that ACS, those ACS aggregates, we're showing you how you might compute those weighted estimates on your own, okay, before you jump into this analysis. So we're reading in the full size of the population for Wisconsin, also from the MIT lab data, but then we're reading in the ACS data to use for further analysis. Once we have that ACS data, I'm sorry, not ACS, once we have the ANES data read in, now we're actually using the survey functions to calculate weighted estimates of each of the means for the non-selected cases and weighted estimates of the variance covariance matrix for all of these Z predictors. Okay, so we're not just grabbing the aggregates from ACS like we did before. This is the kind of code that you could use in R to actually compute weighted estimates of these means and the variance covariance matrix using the ANES data. So we're using the weight prepared by ANES and analyzing the ANES data right here specifically for likely voters in Wisconsin. Okay, so I'm going to run this whole chunk, and what that's going to produce is this vector of weighted means that we need for input and that variance covariance matrix that we also need for input for the MUBP approach. Okay, so once we have those inputs, again, making sure I'm reading in the MUBP functions from the GitHub site. Okay, same stuff that we talked about before with Rebecca for the vaccine example, dependent variable, size of the selected sample, fit my probit model using all those predictors, all those Z predictors. Okay, so that's what this chunk is doing. Okay, same approach as before, take out our proxy based on the linear prediction, use that bs.two-step function to look at the biserial correlation between Y and the predictions of U. Okay, so go ahead and do this. Look at that proxy. Okay, we're kind of shifting everything in our favor here, but now that correlation's up to 0.865. And the reason that's happening is because of those additional political variables that we included as Z's. Ideology and party preference. Very strong predictors of whether or not you're actually going to vote for Trump. Okay, so this is a very strong proxy, correlation of 0.865. Those things that we added as Z's are very strong predictors. And we're going to see what that means for the performance of MUBP in this case. If you have the good fortune of identifying Z's like that are also available in your population data source. Okay, so we really want to see if the method works as well as we would predict that it would work in this case. All right, to calculate MUBP, same approach Rebecca just illustrated. We extract that design matrix of all the Z variables for our selected sample. That's kind of the last piece we need. We remove the intercept, all the same kinds of inputs, the means and variances coming from ANES, the Y, the Z's, the sample size, what we want to do in terms of our draws. And here we're using 1,000 posterior draws. Before we were using 500 in the other application because of the sample size. Here, remember, we have a relatively small sample size. All right, so I'm going to run this chunk where the magic happens based on MUBP, already done with 1,000 draws. Again, the big difference there is the sample size. All right, let's look at that same graph of MUBP against phi. Okay, what's the big difference if we look at this graph? Remember, all those other graphs of MUBP against phi that we've looked at so far, really tight windows, very little uncertainty as a function of phi. Now, as a function of phi, it's really not even clear whether this is curvilinear or linear. But the reason there's so much uncertainty in those draws, the sample size. Okay, before we were talking about 74,000. Now we're talking about 800. Okay, so now we don't have as strong of a sense. But even with that noise, look at the y-axis. Even with that noise, all those MUBP draws are well below zero. Okay, in terms of the negative bias in that particular estimate. Doesn't matter what choice of phi we really use. And in fact, even as we get more non-ignorable, yes, the amount of bias is increasing, but not a whole lot relative to the ignorable case. There's significant bias no matter what you're willing to assume about phi, okay, in this particular application. All right, so now that we have the draws of the MUBP index, we're going to turn around and use those draws to calculate draws of the adjusted proportion. So we're jumping right to step 4 in this particular case. All right, so exact same approach as before, no need to adjust or to standardize or anything like that. We'll go ahead and run this. So the overall adjusted estimate, that posterior draw of the adjusted mean is 0.509 with a 95% credible interval ranging from 0.47 to 0.55. So much tighter interval introduced by the much stronger proxy around the adjustment that we're using. And the nice thing about this interval is that it covers that 48.82% truth. That is what actually happened in Wisconsin. So our argument is that if pollsters would be willing to let go of weighting as the end-all be-all for how to adjust these estimates and not assume that weighting is going to fix up everything, they might see some notable differences in terms of their predictions based on these kinds of polls if they allow for that kind of non-ignorable selection bias. But again, it's important to remember in this example that we had a really strong proxy. And this is just kind of a stress test where if you have that kind of strong proxy, you can get some really good performance. of this particular measure. Okay. Okay, so you see the code's essentially the same. We're just plugging in different data. We're using different sources. That code showed how to compute the weighted aggregates that we need based on the population probability sample, but pretty good performance when you have a strong proxy in this case. Okay, so Rebecca, anything you want to add about that example?
I don't think so. The one thing I will say is that in the interest of transparency, when Brady and I applied this method to a range of different election polls, it didn't perform the same in all of them. So most notably, we applied it to polls from Great Britain, in which it did not appear that like this model was not working. The bias that was observed there did not appear to be this same non-ignorable selection bias as we were seeing in some of the US polls.
Yep. So it's just a reminder that this method does need to be applied separately to every estimate that you're looking at. It's certainly a drawback, especially if you're looking at a ton of different estimates. You have to rethink what that proxy is going to look like, rethink what your Z's are, think carefully about your population data source for every estimate that you want to look at. So admittedly, this is not any kind of magical multivariate solution. It's not a global solution like weights. That's one advantage of using weights. You have the same weights you're applying to every estimate that you're looking at. But if you're willing to put in that time, find the Z's, I think you can learn some things about this potential bias. So, yeah. But yeah, I agree with Rebecca. It's not going to work perfectly in every single situation for sure. Yep. Raphael, yep. Oh, yeah, sure.
So one thing that I think is interesting about this example is that if you look at the ANS data, there are two things about the ANS data. One, the sample size there is even smaller than the poll, right? But another thing, I don't know if this is something that you look into, but another thing that we know about ANS 2020 is that it was heavily criticized for also being very biased. Like if you look at the national estimate, like they severely underestimated Trump vote. I don't know how it was, particularly in Wisconsin. I don't know if you look at that, but like, what does that tell you, right? That like you're using, it is a high quality survey, right? Like no doubt of that. But we know that for this outcome, like a vote choice, it was pretty biased, right? Like, so I don't know. Like, what do you think that like that doesn't matter? It's more about the relationships.
Very well matter, but the focus in using the ANES was to extract good estimates of the Z's. So the Y might have been off, but in terms of the Z's, we were trying to use the weights and the ANES probability sampling to say, these are the best possible estimates we can get of these Z's for likely voters. And that's where this question of, okay, we're using those point estimates, but given the small sample size of the ANES, if we ignore the uncertainty in those estimates of the aggregates for the Z's, is that having an effect on this overall analysis? Because we're assuming that those point estimates based on an even smaller sample were known with certainty, which clearly was not the case given that small sample. So that's where I'm very eager with what Sergio is working on to see how accounting for that uncertainty formally as part of the Bayesian process might change things. So.
Now, just a second question.
Yep.
Other question, comment. So I'm with you. I've been criticizing posters as well for not like, going that extra step. But one thing to note here, right, is that like ANES is not available. Data is not available until like we literally just released ANES a few months ago. So like that wouldn't be available for posters to do that in a pre-election poll, right? And one thing that I think would be interesting is like all your process there, right, or procedures is coming from a single data set. But one thing that I think it's really valuable would be to use, for example, and like that's another thing, right? Like we wouldn't have microdata for that. We would have only population totals, but would be to use the previous election result, because that's like a very it's very correlated, right? But like we'll be able to get that for aggregates, not for the microdata. And even if you have microdata, it'll probably be like a different microdata if you have like the last ANES. And probably would want to use a ACS for all the other variables.
Right. But remember, for the MUBP specifically, we need to be able to estimate those variances and covariances.
Yeah.
We don't have that from the prior election data that would eliminate that as a possible source. That's the problem.
Yeah.
Yeah, so I have done some work with Pew in looking at some of their online probability samples, and it's exactly that situation in which the margins that they use for the weighting come from different data sources, right? Because they have party-related affiliation things from one source and demographics from another source. And so in order to apply this method, we get that as vector of means and proportions from all these different sources, but then we have to make the assumption that that variance matrix in the non-selected sample is the same as in the selected sample. And that's an incredibly strong assumption that is likely not true. And so it degrades the performance of the method. You can still use it with that assumption, but it definitely causes the method to perform less well than if you actually had that covariance matrix.
And for all the reasons that you're mentioning, Raphael, that's why for this particular case study, we looked at many different population sources that may have been at different levels of availability at the time that this poll was conducted. Because I 100% agree with you. Some of these big probability samples, the data are only released, very widely apart. And so you need something that's there, that's timely, that's available. There's a lot, like I would argue that the identification of good population data sources on the Z's is probably the hardest part of this whole methodology. Like then it's, that's the devil in the details thing, but like trying to identify these good population sources is the kicker really here.
Thank you. Thank you.
Other questions on Zoom? Okay. Okay.
So yeah, there is one that Rebecca just already answered. Rebecca, do you want to walk us through the one that you
Sure.
just responded to?
Sure. So there's a good question asking, do we have a variant of this example excluding ideology and party affiliation? And my answer was yes. In the published paper, when we analyzed these data and many other polls, we looked at what if we exclude those, still use ANES, but just use demographic information versus also party and ideology. And then we used multiple different data sources. We looked at a NORC data set as well as CPS, which is, of course, demographics only. And for the most part, what you can see is, of course, the intervals get more narrow when you include party and ideology because the strength of the proxy gets stronger. But none of these, to this point of this discussion that we just had, none of these are really ideal in terms of being available, having all the covariates you want at the time that these polls are going on.
Mm-hmm.
And you can run, another part of my answer was, you could take this R code that we have shown you, and you could just remove the variables that are the party ideology, remove them from the microdata, and remove them from the population margins and covariance matrix, and rerun, and you will see that the intervals will get a lot wider.
Right. Yep, and that's exactly what's shown in that POQ paper. So we'd be happy to share that if you can't find it online. So. Okay, any other questions on this example before we turn to our final piece here? Oh, yeah. Mm-hmm.
So one more weighting question from the chat. Using the unweighted estimates, do you also ignore base weights if you've oversampled some groups?
For this adjustment, yes. The nature of the MUBP adjustment, we would always start with the unweighted estimate and then see how far off that is from the actual population estimate. So the weighted estimate that we used here, those weights were adjusted for baseline probabilities of selection and calibration adjustments that were applied using both census and NHIS data. So, but when you're using the MUBP for adjustment, you would always start with the unweighted estimate based on the non-probability sample. Yep. Yep. Okay. Any other questions? Okay. So let's turn to that last kind of estimate that we're going to talk about. And again, we have a summary slide here that kind of wraps everything up from that particular example. The last kind of piece that we'll talk about in terms of an approach is measures of selection bias for regression coefficients. So somebody asked a question earlier. We've been talking about means and proportions and how to adjust those and evaluate selection bias in those. Can we do the same thing for estimates of associations? And the answer is yes. This was a separate part of this work that we've been looking at. And this gets back to Raphael's earlier question, where if the focus is on estimation of regression coefficients, what if your selected sample that you're using to estimate those coefficients is also biased in terms of the estimates of these relationships. So not just the descriptive quantities that we've been talking about, but what if you're also getting a biased picture of estimates of relationships? And that's why we wanted to see if we could apply the same general proxy pattern mixture model methodology to the case of estimates of regression coefficients. So the focus here is on relationships. So a lot of researchers want to go above and beyond descriptive statistics, obviously, and look at relationships between variables. So thus far in the work that we've been doing, we've developed similar measures of selection bias for estimates of regression coefficients coming from linear regression and coming from probit regression. That's as far as we've got. So all that work was covered by an R21 grant from NIH. Like Rebecca said, we've done some additional work since looking at estimates of treatment effects in clinical trials that are done on volunteers. Rebecca and I are working on this imputation problem where we try to adjust imputation model coefficients for potential selection bias. But there's a rich set of work that could be done in this area to extend these ideas to other types of regression models that we haven't covered yet. This is as far as we've gotten this thus far. So, and then again, just kind of a picture of looking at relationships and the different ways that people might overfit data sets when trying to talk about relationships or when they're looking at stars. Okay, so a very long-standing approach to dealing with bias in estimates of regression coefficients goes back to the Nobel Prize winning work of James Heckman, University of Chicago, who developed the so-called Heckman selection model as a way of adjusting for selection bias in terms of estimating regression model coefficients. The problem with that Heckman selection model approach is without a large number of auxiliary variables or structural model assumptions, the data provide no information about the regression coefficients for unselected cases and how they differ from coefficients for selected cases. So it seems to make sense to look at this again like a sensitivity analysis. Like how different might the coefficients be depending on the nature of the selection mechanism? So the Heckman selection model assumes that you have some latent variable that crosses a threshold, and that latent variable is assumed to have a joint normal distribution with the outcome y, and that L is what drives selection, okay, and that there's some kind of shared distribution between L and y. But proper identification of that model requires unverifiable assumptions and also that approach leaves out subsets of predictors from either the regression model for Y or the model for L for the selection indicator that determines selection. So there's a lot of kind of arbitrariness about the joint selection model that's being fitted there. And Rod's talked a lot about this in his book on missing data. Furthermore, the Heckman selection modeling approach requires microdata on the selected and the non-selected cases. We have to have a data set that has microdata on predictors so that we can predict L in the first place using the available microdata. So the approach that we've developed for regression models is simpler analytically, it's simpler computationally, and it doesn't require the presence of microdata for the non-selected cases. Like the measures we've talked about so far, we just need aggregates on the non-selected cases. Now, the devil in the details in this case is what aggregates exactly do we need for those non-selected cases? So same kind of basic setup. You have data on a non-probability sample. You have your dependent variable of interest y. You have your predictor variable z that are of direct interest as predictors of y. So your objective, your scientific objective, is to estimate the coefficients for z in a model predicting y. That's the goal of your study. Okay, you want to estimate those coefficients for z, and you're worried that they may be prone to selection bias. Okay, so unique to this methodology for regression is the presence of these additional auxiliary variables, defined, which we call A here, that are not of direct scientific interest in the model that you're trying to fit, but are still related to Y after you fit a model conditioning on Z. So you think about that and you're like, well, why would you just include those A's in the same model of interest? These might be things like covariates and sociodemographic subgroup analyses, or post-treatment outcomes related to Y in clinical trials, or other endogenous variables that you might be fitting separate models for, but you wouldn't be including those other dependent variables as predictors in this model of interest. So they're just additional auxiliary variables that primarily serve the role of being predictive or having some information about Y once you condition on Z. And again, identification of these, Rebecca and I have had countless conversations about, where do you find these A's? How do they compare to the Z's? We're working on that with respect to a paper right now. It's always an interesting discussion. But this methodology hinges on the presence of those A's that serve as good predictors of Y after you condition on Z. And like we've talked about with the method so far, you also have aggregate population information for both the Z's and the A's from some kind of probability sample or some other population data source. So not just the Z's, but both the Z's and the A's. Okay. So the way this works in general, using the non-probability sample, you would regress Y on both Z and A. Again, the goal is to look at the coefficients for Z, but to use this methodology, we would regress Y on both Z and A, and you create that auxiliary proxy X using only the coefficients for A from that particular model. So you're basing your proxy X on that additional set of predictors that could be explaining Y after you've already conditioned on Z. So X is defined entirely by the linear combination that involves the regression coefficients for the A variables in that model fitted to the non-probability sample. So there's just a simple example down below where if there's one Z and one A variable that you've identified and your focus is on beta Z, the proxy X would be formed based on the estimate of the regression coefficient for A coming from that model that regresses Y on both Z and A fitted to the selected non-probability sample. Okay, so that's the difference in this approach here. And as with the earlier indices, we do allow for those additional V covariates that could be orthogonal to both X and Y after conditioning on Z, but could be predictive of S as the selection indicator. Okay, so that's the same kind of basic allowance there. So same kind of pattern mixture model setup, but now we're conditioning on Z. Okay, so we're looking at the means and the variances and covariances of both X and Y given the regression framework because we're conditioning on Z. So you can see how the means are defined by the regressions of X on Z and Y on Z. Okay, we're conditioning on Z when specifying the pattern mixture model. We're also looking at the variances of X and Y and the covariances of X and Y after conditioning on Z. So now the proxy pattern mixture model is conditioning on Z, and it still allows for different regression coefficients, different variances and covariances after we condition on Z for the selected and the non-selected cases. And just to be clear about this kind of funky looking subscript notation here, the beta YZ dot Z, those are the regression coefficients for the Z predictors in a model for Y, the first subscript letter given Z. Okay, so the dot Z is like what we're conditioning on, but we want to see the coefficients for those Z predictors. Same idea, Y0 dot Z is the intercept in a model for Y given Z. So that's what that notation means here. And accompanying that specification is this model for that selection indicator, exact same setup, but now we're looking at conditioning on X, Y, Z, and V in this particular setup. Okay, but other than that, exact same setup, exact same kind of sensitivity parameter. The key difference is that we're now conditioning on Z in this specification. And it's the exact same sensitivity analysis as before. We can vary phi from 0 to 1 to capture the range of assumptions about the ignorability. Okay. So from this, and we show kind of where this comes from in a separate paper, we get measures of unadjusted bias relative to the coefficients that we would see for the non-selected cases. So we've done a bang-up job of creating these acronyms. Now we have something called MUBNS. Again, don't really know how you say that out loud, but the key difference here is that the way this setup works, we're not looking at the difference between the estimate that we see for the selected sample and the population. In this setup, it's the difference between the estimate that we see for the selected sample and the estimate that we would see for the non-selected cases, all the zeros in the rest of the population. Now, if that sampling fraction is tiny and the population is huge, those beta estimates for 0 may as well be what we see for the rest of the population. But the way the math works out here, it is the difference between the selected and non-selected cases, and that's why we use this kind of NS notation. And again, same basic intuition. There's a scaling factor that captures the correlation of that auxiliary proxy X with Y after conditioning on Z. That's the big difference. It's a conditional correlation. And then we see the differences between the selected and the non-selected cases in terms of the regression of the proxy on Z. That's the piece that is going to give us an idea of the amount of bias in the estimates of the regression coefficients using that auxiliary proxy. Okay. And then we scale that difference after conditioning on Z. Okay. So we would interpret these as the difference in the regression coefficients between the non-probability estimates and the rest of the population. Okay. Not compared to the full population estimates. That's the difference. Selected versus non-selected. Okay. And there's a paper here if you want to read more about these different details. But the concept, the intuition, same basic idea. We're just conditioning on Z throughout the process as the primary predictors of interest. Okay. So as I was mentioning, you can drop the NS from this wonderful acronym and compute simple measures of unadjusted bias relative to the population, not relative to the non-selected cases, just by multiplying those MUBNS bias measures by the overall non-selection rate. So if that non-selection rate for the non-probability sample approaches 1, then you can see you're multiplying the MUBNS by 1. Otherwise, you're multiplying by whatever that non-selection rate was to get these actual measures of unadjusted bias relative to the population. An important check that we looked at is that if you fit a regression model that only includes the intercept, like a mean-only model, you should get exactly what we saw for SMUB because you're just looking at a mean. And that was, in fact, the case. So this simplifies to the SMUB if you're just fitting an intercept-only model. And same ideas we've looked at in the other 3 examples. To adjust your inferences for the selection bias, you would just subtract the MUB indices or draws of them from the coefficients based on the selected sample to get your adjusted estimates of the population regression coefficients. And just as before, we need to have those strong conditional correlations of the auxiliary proxy with Y after conditioning on Z. Same idea, we need those to be strong for improving the performance. And as I mentioned earlier, you can extend this to probit regression models as well, using the same kind of approach that we use for binary individual variables. So we looked at some simulation studies as a part of this paper. As we expected, stronger conditional correlations between the A's and the Y are important for improved performance. This choice of 0.5 for phi just continues to work well in all these applications. We say it's kind of capturing reality in some sense. And when selection's a function of Y, the MUBNS measures with higher phi values tend to perform better as expected. Bayesian credible intervals for these measures of selection bias based on those uniform 0-1 draws of phi tend to offer good coverage of the actual differences in the coefficients across many different scenarios. And that good coverage isn't coming from the fact that the credible intervals are just really wide. They're also relatively narrow and providing good coverage. So it seems like the method is fairly efficient as well. So we're going to look at our final example is how to fit this kind of regression model. The application here is looking at a dependent variable that captures the number of months employed in the past year. And we kind of handpicked a population that is very selected, smartphone users with less than high school education in a particular survey. So for that subpopulation, we want to fit a regression model predicting the number of months employed in the last year as a function of selected Z variables. Because I do want to save some time before 1 for conclusions from Rebecca, I'm just going to highlight certain parts of the code here to illustrate how we carry this out. Again, very briefly, this was a hypothetical non-probability sample based on smartphone users, those with less than high school education. The predictors of interest are age and gender. So I'm restricting the set of Z's to be those that are of specific scientific interest, age and gender, in predicting number of months worked in the past year. That also leaves room for several other A variables that we could consider. And this is, again, an important part of this methodology. So this sample is about 2,977. The Y variable is number of months worked in the past year. The predictors are age and gender. And these additional A variables that are auxiliary but not of interest for the specific question, but likely still related to the outcome after we condition on those Z's, included race, ethnicity, income, marital status, region of the US, current employment, and presence of children under 16 in the household. So I know those all sound like good covariates in this kind of model, but we wanted to illustrate the performance here if we treat those like they're A variables. And again, the idea here is that only age and gender are of direct interest, and we want to adjust estimates of the coefficients for age and gender for potential selection bias using these other A's. Okay. So it's a kind of artificial example, but we do have the full population available because we're defining this subsample from an entire survey data set, this National Survey of Family Growth. So what we can do is calculate necessary summary statistics for the non-selected cases using these data, but we also have some sense of a truth because we have the full sample. So we know what those regression coefficients should look like, and we can use that for evaluation as well. Okay. We also know the sampling fraction. We know what fraction of the full NSFG survey data is defined by this non-probability selected subset. So that allows us to compute the MUB measures and again, evaluate their overall performance. So we're going to run analyses for the selected and non-selected data sets as part of the example. We're going to look at regression models to get a sense of the true bias in the coefficients because we know what those true coefficients are. We're going to calculate those MUB indices for each of our different regression coefficients. And then we're going to adjust estimates of those coefficients given draws from that overall Bayesian approach. Okay. So I'm just, like I said, going to go through this fourth example pretty quickly. The code is all commented so you can see everything that's going on here. So we're starting, just read in that full NSFG sample where, again, we know the details. Reminder about having all the predictors and everything harmonized, in this case, both the Z and the A variables. Okay, so we do all this recoding to create all the dummy variables to start with for these different categories. We're going to divide the NSFG up into these selected and non-selected samples. Okay, so we have what we're calling SP1 and SP0. And this initial check is just to show what is the known bias in these coefficients. So we want to start with saying, we know what the bias is. That's our target. We want to see how well the method does relative to the known bias and the known differences between selected and non-selected. So that's all this step is doing here, is giving us initial estimates of the differences between the selected and non-selected cases. And you can see in the tables that are showing up here how the coefficients, especially for male, are pretty different between selected and non-selected. And that's what we're trying to recover from these kinds of adjustments. Okay. We can also look at the full population model and see how the selected sample differs from what's known for the full population, where again, there are some pretty big differences. So again, artificial case where we know what that truth is, but we want to do that as part of the evaluation. The regression functions are on the same GitHub site. So I can just run this to source in those particular functions. I get my summary statistics for the non-selected cases, in this case from the NSFG data set. So I'm doing that directly from those non-selected cases. That's what this step is doing, getting all my means, my variances, and my covariances. And I'm putting those together into a list, much like the SMUB code was working for the non-selected cases. I get those same summary statistics for the selected sample. Okay, so my means, my variances, my covariances, save those in a list in stat selected. Okay, one of the functions that's available in the code is to do those point estimates of the MUB calculations, and all we input are the stats for the selected, the stats for the not selected, and then the number of Z variables. That's an additional argument that's important for this analysis, is being explicit about how many predictors you're actually working with in that comparison. Okay. Okay, so I go ahead and run that analysis for the point estimates, and you can see for each of the 4 regression coefficients that we're trying to estimate, the value of the index, so the bias measure, when phi is 0, when phi is 0.5, and when phi is 1. So we get that full range of potential bias in each of these estimates. And again, in this particular case, we can see evidence that all 4 of those coefficients are subject to some form of selection bias, just based on plugging in and looking at these point estimates, because none of those wide intervals between 0 and 1 seem like they include 0 for those bias measures. Okay. All right. You could also look at the sensitivity of those to different choices of phi. This is just illustrating how you could pick 0.2, 0.5, and 0.8 as alternative choices for phi and look at what those bias measures look like. So you can really pick whatever value of phi you want because, again, it's an arbitrary sensitivity parameter. Okay? So now we can use this MUB reg Bayes function to implement the fully Bayesian approach to getting estimates of those coefficients and then adjusting our estimates based on the non-probability sample given those draws. So I'm doing all of that in one step here in this particular chunk. All right, so it might take a little second to run. Then we come up with adjustments of each of those coefficients. And so initially you find here the median, the 2.5 percentile, and the 97.5 percentile of each of those individual coefficients. Okay, so that's giving me inference about each of those coefficients after applying this kind of adjustment. So again, I just jumped right to step 4 and adjusted the estimates themselves there for each of the regression coefficients.
Brady, those are the intervals for the index, not the adjustment is next.
These are okay. I'm sorry. Yeah, excuse me. Those are the bias index values. I apologize. There is a step 4 later in the code. So right. So these are the bias indices, and again, we would look at these intervals to see if they include 0 or not. And only in the case of that 4th coefficient do we see that the 95% credible interval does include 0. So it seems like that 4th coefficient may not be as subject to bias. Sorry, I apologize for that. So there is a step 4 here where then we're taking those draws and again doing that adjustment to each of the individual coefficients to see what those adjusted coefficients look like. So I'm just going to go ahead and run this chunk here. And that gives you for each of the different coefficients their point estimates. This is just showing the actual coefficients for the true population. But you can get summaries here. I'm going to try to bring those up. Yeah, let's see here. Sorry, this is just showing for the intercept exclusively. Yeah, this is just showing for the intercept here. So you're getting the median, you're getting the lower bound and the upper bound, and this is the adjusted estimate of that particular coefficient. Okay, so this is giving you an idea of what that adjusted coefficient looks like. Again, relative to the truth. Let me see.
That first one, that one's the intercept, and then the next one is the male coefficient.
Okay, I was trying to remember what we did here. Yeah, so okay, this is the intercept, this is the male coefficient, right? Because they're both labeled as B0s.
They're labeled as B0 because 0 is for non-selected here, right? So that's not like beta 0, the intercept.
Yeah, so we're not showing all 4 coefficients. We're just kind of hand picking the ones that we want to look at here. But these were the 2 that were most subject to bias. Okay, so right, so intercept, male coefficient, and again, the idea is that the adjustment is bringing those coefficients closer to what we knew is the truth based on the full NSFG sample. Yeah, sorry about that confusion there. So, okay. So we didn't look at the same adjustment for the other 2 coefficients, but we just focused on the ones that seem like they had the most bias. So I know we went through that quickly, but the idea is you can extend the basic methodology to a regression setting where you identify particular predictors of interest. The key point there is just having these additional A variables that provide some information about Y after you condition on Z. So, okay, any questions about that regression example before we jump to our kind of final conclusions here about these approaches? Any questions about that regression case? Okay. All right, so I will turn it back over to Rebecca for the final kind of concluding comments about what we've seen here today. So,
sure. Thanks, Brady. So very quick wrap up, just 2 slides. So first, a checklist of what you need to implement these measures. So of course, you need all of the R code, the functions, and the various packages. And then in terms of data, you need informative auxiliary variables. So you need those Z variables to be able to predict your Y variables, and you need them to be available both in, of course, your non-probability sample and also in the population data source. With that caveat that remembering in the regression case, it's extra complicated because they have to be sort of extra Z variables that you're not interested in the regression coefficients of those variables, but you need additional ones to be able to create the proxy. And we, as a rule of thumb, tend to say that we want that correlation, the strength of the proxy, the square root of the R squared from the linear regression, to be 0.3 or higher for these methods to be able to produce reasonably interpretable intervals. You need that data in the target population, means or means, variances, and covariances in the case of the binary, or if you're going to be Bayesian. And this is, of course, the hardest step, although with the reminder that you need similar information to do standard weighting that assumes ignorability. And then ideally, if you can be Bayesian, we recommend that you are Bayesian about it, because then it allows you to sort of instantly see the effect of that varying of the sensitivity parameter instead of just looking at a bunch of different point estimates. It also incorporates the uncertainty in the creation of the proxy. Instead of just plugging into a fitted regression equation, it's incorporating variability in those beta hats themselves coming out of the regression that creates the proxy. And then we have a couple of anticipated FAQs, things that we often get asked. So the first one, what value of the sensitivity parameter is optimal? Of course, we do not know. The observed data don't have anything to tell us about the sensitivity parameter. We've said this multiple times. We like 0.5 as a sort of compromise. It happens to be almost the exact right answer in the case of vaccination status and the household pulse survey, but that is not, of course, always going to be the case. So looking at the range is what we recommend, but if you need to pick one number, 0.5 is a good starting point. Another anticipated question is, what if the credible intervals are really wide? Well, this is going to happen if you have a weak proxy. And so you, unfortunately, often means there's not much you can do about it because you've already collected the data. But if you can look for additional Z variables that might increase the strength of the model that creates the proxy, then you may be able to get tighter credible intervals. And then finally, some people who are less familiar with the Bayesian framework often look at the credible intervals and say, those aren't symmetric. What's going on? And that's because they're credible intervals. They're not constructed in the same way as a standard confidence interval. And so they are, in fact, the 2.5 and 97.5 percentiles of a large set of simulated draws. And we don't actually anticipate them to be symmetric. They're almost never symmetric. And in fact, if you look at the median, it will often be quite a bit closer to the 0 end of the distribution than the 1 end of the distribution. That's it. We would love to take any additional questions, although I recognize it is 1:03.
Yeah, we know it's a lot, so it's a lot of material. So thanks to everybody on Zoom who hung in here for all these 4 hours. But yeah, any general questions, comments, thoughts? We'd be happy to take those at this point. So. Oh yeah. So as part of all the PDHP workshops, you will be receiving a feedback survey that just asks you some questions about this workshop, allows you to give some feedback about the workshops and thoughts, and then also provide us with more general comments about other topics that you might like to see in the future. So stay tuned for that feedback survey, and we'd love to get that from you because it definitely helps us to make decisions about future programming and everything. So stay tuned to your email for that survey. And if you don't mind, please do give us some feedback if you get a chance about the workshop. And of course, Rebecca and I, like we said, we'd love to hear from you by way of follow-up by email. If you have any other questions or you'd like to try to apply these things to your own data, we'd love to work with you on that. So, yep.
The link to that survey is in the chat right now, and I'll also send it by email, like Brady said.
Okay, but yeah, any general questions or comments? Okay, well, yeah, thanks again, everybody. Thanks again to Rebecca for joining us remotely and providing all of her excellent insight today. So, yeah, hope everybody enjoyed this, and feel free to reach out if you have any questions in the future when you're trying to work with this. So,
Thanks,
okay,
everyone.
thank you.